It's live. Okay. Good morning. Today we have Denis Andrault as a speaker, and he brought with him very nice weather for a change, because normally we have rain around here. Thank you. And he got his PhD back in 1990 from Paris. I think in 98 he got the habilitation. And then he had a couple of postdocs in the 90s, first in Canada and then in Paris, after which time he became an associate professor in Paris 7. And then moved in 2006 to Clermont-Ferrand, where he has been ever since as a professor. His interests are deep mantle phases, deep mantle melting, anything about deep mantle, I guess is a fair statement. And today he will talk about the thermal state of the deep Earth along its history. It's all yours.
Thank you very much. Thank you, Owen. Thank you for the invitation to present a talk here. I'm very happy to give you some ideas about what we've been doing in the last 5 years, maybe, let's say. So many people have been discussing the thermal state of the deep Earth using different methods. I'm a mineral physicist, so I try to stick on what I know and try to give the best constraints we can get from mineral physics, and to try to restrain a little bit the possibilities we have for the early Earth. And I will be talking about the very early Earth just after the magma ocean, and then how it evolves from then. So this is my collaborators in Laboratoire Magma Volcan, different people here with whom I'm working every day. And with many visits in Grenoble, synchrotron to do X-ray diffraction in the ID27 beamline, and recently to also to the Mossbauer beamline, but I'm not going to be presenting much about the Mossbauer result in this talk. And we recently set up a large volume press apparatus in Soleil with in situ X-ray diffraction measurements, which happens to be working very well. And other people from different labs will become my colleagues very often. So what I will be doing is my strategy here is to try to refine the thermochemical state very early, just after the moon forming impact. And I have this idea that this is going to set everything about how the Earth has evolved until today. Like there is a first time, there is a first starting point, and it's still very controversial in some aspects. And I present here 3 different cartoons. One is like the classical cartoon, where you have a magma ocean that has been to a certain depth due to the impact, the moon forming impact, and that has crystallized then relatively homogeneously from the bottom to the top. Another model here is the Basal magma ocean model that you've been probably aware and heard about. It's a more recent model that is completely different in the sense that you have a solidification layer in the middle, and that has huge implications for the structure, inherited structure of the Earth, and an intermediate model here, where you can start from this kind of solidification process, and you have overturns that make some segregation, some chemical segregation. But that's on the second step. And since we are interested to know what's the starting point in terms of thermal and chemistry, they have different applications, those 3 models. So I will be talking about which model could fit better to the mineral physics constraints. And then once the starting point is defined, I will see what's the implications of the cooling, the secular cooling. So first of all, I would like to try to convince you about that point, which is here, because there are 2 points. If they are fully correlated one to another, it's the core temperature the core temperature could have been very high or not. And this is an enormous amount of heat that we need to decide where it's been, if it remains in the core or if it flows away very fast. So there was this modeling about how much heat flux can go through the adiabatic profile in the magma ocean using very simple relations. And there is a profile here, so there is a certain slope for the temperature profile and a certain conductivity, which depends on the conductive and the convective conductivity. It happens that the viscosity of the lower mantle is low. I will show some data later about it. So if you calculate the flux that is going out from the Earth when it was completely molten, if it was completely molten, it's an extremely high amount of heat flux that can travel through the adiabat, and it's already such a large amount that if you would want to insulate a part in the deep Earth from the rest of the Earth, you would need to increase the profile, and that's basically impossible to my point of view, and I think to the point of view also of the previous author. So the conclusion is this one, is that in order to stop the Earth's cooling, it looks evident, but I will come back to that later. In order to create a solid Earth, because this is what we want to get now, in order to create a solid Earth, you will have to lower down the core temperature. Because if the temperature of the core is very high, then the heat flux will be high and you will be molten everything. So you have to create something solid somewhere. And the magma ocean, the liquid, cannot stop the core cooling. You will see the implications of that in a minute. So now I will use the melting curves. I will show some experimental results, how we do those measurements in a while. But first, I'm putting the major constraints on the temperature limits we have with the basic curve. So this is the melting curve of the major phase of the deep mantle, the Bridgmanite. And the Bridgmanite is also the liquidus phase. It's the first phase to appear when you crystallize the Earth. So you cannot have the temperature of the temperature of the mantle once you had done this major impact and you cool it down. This is the upper limit of the temperature profile of anything in the Earth after the Earth has been solidified. And so the experimental work is not that important. It's controversial here. But the models are very good. There is the different types of ab initio calculations and also some shock experiments followed by some thermodynamical modeling. And this is basically what we should obtain for what is proposed, what is for the Bridgmanite melting curve. And I argue based on the previous diagram here that this is the maximum temperature you can get when the Earth starts to solidify. So this temperature here is a maximum temperature for the core after the moon forming impact. But in fact, if you look more carefully on the phase diagram, this temperature is already too high. Because what really happens if you want to make a layer of material, you don't want to create you don't have the MgSiO3 alone. You have a mixture of phases with the ferropaque clays, the Bridgmanite, and the calcium perovskite. So you will crystallize at the liquidus. There's been a big discussion about where is the liquidus of the pyrotic mantle, the pyrotic mantle, the chondritic mantle, and I'm not going to go too far in those discussions. What I can say here is I think there is two models remaining alive. One other model is been withdrawn. One is the possibility that the curves of the liquidus are relatively flat based on our measurements that I will show you in a minute. And it could be more curved like this. It's ab initio experiments from Stickstrud 2009. And the temperature of the Liquidus here or there are not that high. Means when you start, when you have a magma ocean and you cool it down and you start crystallizing the mantle, you start making it's temperatures that are actually relatively low, like 400, 700, 4,750 K, or even lower here, 4,400. There was a Liquidus proposed in a good article also from Geophysical et al. It happens that this Liquidus that's been used in many calculations and used to say that the core could have been very hot very early on, it happens to be the melting curve of bridgemanite. And when in this group, when they show the pictures with the samples in the center, it's full bridgemanite. So the melting curve here is the melting curve they proposed as a Liquidus of periodite. It's in fact a very nice measurement of the bridgemanite melting curve here, which is there. And I think this second work here, this second curve is more like another M member with linear or curved, and I will use those two for the discussions. So we are there. How strong are those experimental constraints? How much chemical fractionation can affect the picture? Because here we are in a homogeneous mantle case where we see the Liquidus and the solidus for an entire mantle. And this will give me room here to go in the showing how we do the experiments, how we do the measurements of the solidus and the Liquidus, and how we get there, how much error is there. Because the error on those curves are going to be directly translated into an error of what we know on the thermostat of the Earth, primarily after the magma ocean crystallization. So what we do now is we use, for a long time already, we use a diffraction beamline. For diamond cell experiments, we start now almost exclusively with glass as a starting material. Glass that we prepare with using the levitation method, because on a level of 10, 20 micron of the laser spot and a couple microns of the diffraction spot, we want homogeneity. Homogeneity is only achieved when we do the glasses. It can be chondritic. Our chondritic is not far from pyrolytic type mantle. We use salt as pressure medium. They may not be excellent, but they are very refractory at high pressure, so it's very convenient for our system. We could use argon. We tried several times. It's not very different. Thermal temperature is measured classically using the black body emission or gray body emission, but we have used for many years now reflective objectives, missing a F here, reflecting objectives which prevents from chromatic aberration. It's very useful to our opinion, especially on a beamline where the position of the sample is dictated by the X-rays, not detected by the optical system. So it prevents from problems in the temperature measurements. And it appears, because here I'm more concerned in this talk by the Liquidus determination. The solidus is a secondary importance in this thing. The Liquidus is more difficult to measure than the solidus. The solidus is the first change in the mineralogy with a loss of some diffraction peaks or rapid change in solidus is relatively easy to determine. Liquidus is more difficult because you want to see the last disappearance of a phase in a given composition. Or if you go from the melt and you cool down the sample, which is possible using the laser rating, you want to see the first appearance of the diffraction peaks, but there are temperature gradients which make it difficult. So yes, determination of Liquidus is not very easy, or it's difficult in the diamond cell. We found that the best criterion we had was this one. Peak reappearance on the quenching temperature means, of course, we follow progressively the disappearance of the peak. But when everything is almost molten, because you still have a few grains that crystallize close to the pressure medium, when you decrease temperature and many peaks reappear, this really means that you've been melting almost everything or everything. So this is the system we use. These are the telescopes. This is the old picture, but this picture is easier to see what's happening than the new ones, because we now use vertical lasers, but the picture is difficult to make. We don't see much. So these are the reflective objectives. they're usually pushed in, especially that from the front, where the mirror here is drilled, so you can keep the temperature measurements during the X-ray measurements. So they're out at the moment, but they're pushed in. And the back here, this is the diamond cell. The back temperature measurement is done only in between X-ray measurements, but the X-ray measurements last for 5 to 10 seconds, so it's not such a big problem. And the lasers are focused on the sample. This is the kind of temperature measurement we obtain. We look at this is the entrance of the spectrometer. So the laser spot here, similar to this one, similar temperature is misaligned, but this is classical. Everyone has been doing some laser heating experiments know that this is not so difficult to do. This is well aligned, and this is well aligned too. These are some temperature measurements I show for extremely high temperature, like 5,000 or 6,000 K. This is the raw data. So we correct the raw data from the transfer function from the experimental setup, and we get those fits. And this is the two-color fits, which uses a pixel or region one by one, and showing that the pattern is extremely good. This is regular, means thanks to those reflective objectives, changing one cell to another makes basically the same fit extremely well. As soon as you have enough intensity, of course, on a different part of the pattern, then you get an extremely nice fit on the range of energy of the wavelength here that is relatively comfortable. So we're relatively comfortable with that. Everyone knows now, if we want to go in the details, of course, that there is some more difficulties actually to measure the pressure, because if you don't want to mix calibrant with your sample, we know the sample pressure increases when you do the laser heating, but you can correct this effect by calculating some thermal pressure. But it makes an error on the final pressure at high temperature. So this is a sketch here. This is the diffraction pattern with bridgemanite diffraction peaks here and the KCl. The KCl, we keep them intense in purpose so that we are sure the sample is thin and that the vertical gradient from one diamond to the other one are minimized. So it's not noise to opinion, it's the fact that it's good that they stay there because it means the sample is well insulated from the diamonds. And I don't show you the one in between because there's nothing on it. There's no bridgemanite. This is after melting. We see those peaks are now a couple points here and there. It's recrystallized. Here it was not molten yet. So the peaks arise from the glass crystallization, and here the peaks are from quench. And this is the shape of sample we obtain. This is a second place where we've done the melting before. So I'm back to the figures, same figure than previously. This is the Liquidus here and the ab initio and experimental. And these are the temperature we should get for the early core when when the bridgemanite grains will start crystallizing, and this in the couple slide afterward I will start from. But first, I want to know if you have any urgent comment. Yeah?
This is a very basic question. I'm just trying to understand, how do you think about what the definition of the core mantle boundary is in early time? I'm imagining from your impact with the moon, you have a metallic core, but then you still have a liquid outer core, and then where's the definition of the mantle come in? And then, so how do you put that line with pressure? Sorry for such a basic question, but I just don't understand.
I assume that the core segregation is faster, is the first step, because also it brings a lot of energy to the deep earth. So when you segregate the core, which should be a first step, I understand your question. I understand your question. In case you don't melt completely the Earth, in case you don't melt completely the Earth with the moon forming impact, then the temperature of the core should be even lower to whatever I will say later on or now. This is a maximum core temperature if everything has been molten. So if everything has been molten, then all the iron has gone down. If you want to melt the Earth only partially and you want to make a diapirs that go down, then those temperatures are never achieved. And so I can use that argument later on to say, so this is the maximum temperature you can get. I'm interested by the maximum temperature you can get because that defines how the things should evolve until today. But if it's lower temperature, then it's even easier for the arguments I want to develop. So once some grains occur, you can model it more easily. And we've done a one-dimensional model. One dimension is used for several reasons. We've done one-dimensional model to track the mechanism of magma ocean solidification and achievement of a solid mantle. Why did we use a one-dimension model? In that work here, we use a one dimension because we can use precisely the true values of everything, of the thermal conductivity, of the viscosity, of the turbulence, of the heat flow, and of the. Of course, it doesn't model well the lateral variation, but remember that the mantle viscosity when it's molten, it's about water. So you have water all around, and so the convection length is extremely short. It's like a couple millimeters or a centimeter. So there is no big variation laterally. So the assumption of one-dimensional cooling is better, is reasonable. So what we've found, and you will see that it's been found before, and as soon as you start heating and starting to make the bridgemanite, you make a bridgemanite somewhere and you start crystallizing until you reach the viscous transition. The viscous transition is when you have 30, 40% of liquid and 50, 60, 70%, maybe 60, 70% of grains that stop and that change completely the viscosity and that stop such a turbulent convection. And when you melt the Earth completely and you cool it down, you reach a point here where it's the starting point of a solid mantle, solidified mantle, of a viscous mantle. And it happens that when we model that, without here any chemical fractionation, I agree, without segregating, I will discuss this a little bit later on, you reach a point where after 150 million years, whatever is the core temperature initially, I will show you in the right diagrams, you reach a point where you have a mushy mantle everywhere that is solidified from the surface to the core. With a temperature here of the core, every heat, and this is the diagram here, whatever temperature we start for the core initially up to 7,000 K, and you can put more, this heat is going to go away from the core. As I mentioned from the first diagram I showed you, nothing can stop a hot core when the mantle is liquid. So whatever is the initial temperature, you have to cool down that core to the point here where you start the viscous transition. So here we have different models of solidus, liquidus. So this is why the reason the three different curves don't go to the same point. But in a short time, you will reach that point where the core is having a temperature close to this viscous transition. And the mantle temperature is going to be along this line in between the solidus and the liquidus, where you have the viscous transition, and the mantle gets solid, partially solid as a mush. And this is the second starting point. And I think whatever is the impact you can get, whatever the energy you can get to the Earth, this is the starting point of the cooling during the Archean and afterwards. And I want to come back to the question you asked, maybe if I understood it properly. If you have less energy initially and you don't put the core to 7,000 K, then you may have a temperature profile with a core that is slightly lower. And true, in this case, the core segregation will take a little bit more time and will be slightly different in its process. But this is the maximum temperature we achieve with a hot Earth. With a planet of the size of the Earth having a major impact will probably reach that point anyway, whatever you do. our argument here, and we may discuss it later on. And as I mentioned before, this is not new. This has been proposed as early as in 1991 in the Caltech group. You can see that diagram. It's basically the same. There is a temperature here going all through between the solidus and the liquidus. And this is also Stixrud has modeled this also with a temperature profile that is going there in between the solidus and the liquidus. And so with a profile that is there. So now let me go, so this is summaries of what we've been discussed here, the sketch, but I want to focus on that part. I didn't talk at all about cumulative fractionation yet. So it may be important to say what fractional crystallization, which is a separation between the solid and the liquid phases. How can it affect the thermal state? Maybe I will have trouble to talk exactly about the chemical state and how it's structured now because there are controversy, but how the thermal state at least can be affected by a large fractional crystallization early on. So there was a talk, I'm collaborating with this work. There was a talk recently at the AHU on the viscosity. Now the viscosity of the mantle has been remeasured, measuring the viscosity of Avrion members for molten forsterite and molten ansatite and the different components. This is using the falling sphere method and to very high temperatures. And this is the profile of the viscosity you get along the KLB1 liquidus, the one I showed you before from Stixrud. And the conjugate liquidus, this is and you see the viscosity is very low. It's 10 to the minus 1 to 10 to the minus 2, so close to water everywhere when you have a molten mantle. So I'm showing this because what you want is you want to segregate grains and bridgemanite grains from a viscous material. So you have equations for that has been developed by Solomatov and Stevenson and others. And it's true that there is a possible fractionation. So this is again along the liquidus. We look at the possibility to segregate the bridgemanite grains because they are denser compared to the liquids. And in a very deep mantle, and this is for a given heat flux, a given cooling rate, this is the critical diameter size because what you want is to build grains of bridgemanite big enough so that they can sedimentate. I don't go into all details. But it's very close to the limit, and that was already a conclusion of Solomatov and Stevenson long ago. It's very close to the limit between equilibrium of crystallization and fractional crystallization, which means close to the limit means probably not much chemical segregation, maybe a little bit, but not so much. These are different models of temperature again, and here different colors correspond to different composition of material that could segregate or not compared to the metals. So maybe there may be some fractional crystallization, not too much, but it's not going to affect so much the temperature of the core afterwards, because anyway you have to reach a liquidus first to create some grains that may be fractionated enough to produce a solid layer here to sustain a thermal gradient. But you need some of the bridgemanite grains to build a layer, and so that's not going to affect so much. Neither the temperature of the core may be a little bit here, and the temperature profile in the early mantle will finally be along the solidus, and it's not going to be a dramatic change to my view. Here again, I'm not talking about what can occur close to the surface of the Earth, where some liquid may segregate more efficiently, especially if the Earth is covered by an early atmosphere, and that can affect. But this is not a process I will investigate here. So we're getting there. We're getting there, and that's very strong in implications, as I will show. Means whatever is the initial core temperature, if you look at the CMB temperature, so the core temperature, the CMB, or the mantle temperature, the CMB early on, and I put here the age of the Earth, And here it's in between the liquidus and the solidus. Basically, here is the liquidus. It's a range of, because there is controversy exactly where is the liquidus, where is the solidus. So I've put here a range of mantle partial melting temperatures here with everything crystallized here, everything molten here. And so this is the post-moon forming impact initial Sembe temperature that are here. And I have another funny transparent here. Do you agree or not? But as soon as you say okay, I will go to implications and then that. So, yes?
Did you assume there's no basal magma ocean?
It will come. I assume nothing for the moment. I just.
But your curves, your geotherms through time look like they intersect the. Look, they're gentler slopes. The red curves are lower slopes.
I didn't assume anything. I just checked for two different models when bridgemanite will crystallize. I just mentioned that bridgemanite can eventually segregate down. There is some question about how the melt can be denser than the solid, but in order to make a melt denser than the solid, you need to crystallize enough bridgemanite to make them go down compared to something else. I don't think you can segregate a dense liquid compared to a lighter liquid in such a turbulent system. So you need to, so I didn't consider anything yet about that subject, but I will. So if you not so much, because there's no one available than this one. So here, yes, you may create some grains of bridgemanite here first, but then the bridgemanite, are they denser or less dense? They're supposed to be denser at the first steps of the crystallization because the liquid is not yet enriched in iron, so pyrolytic liquid is less dense than the bridgemanite. So yes, in this case, if you assume that fractional crystallization occur, they would go down, the bridgemanite grains, and remelt and thing until you create here a layer or something. But the layer, I will talk about the neutrally buoyant in a minute. Neutrally buoyant, but neutrally buoyant you can, but you need to create here enough bridgemanite so the core is already reaching that temperature. So you need to build here, if you want to build a layer, the core is already there, because the core cannot be. This liquid anisotrope, by the way, is very steep. It's not. I didn't mention that reference. The Celtic group, the Thomas and Asimov, the liquid anisotrope for the periodic mantle, it's less steep than the one used in this diagram. So the thing is a little bit more flat, as I showed in the diagram. Yes. In which slide? I won't agree about 2, 2.5 or something. I won't agree. This will be 5 times a third implication. Yes, I think the opposite. I think the temperature profile early on may have some implication on when the transition from stagnant lead to modern plaque tectonic occurred, but not the other way around. But so implication 1, there is no basal magma ocean, or I should say everything's been shown, but I will give more details. But everything shown here imply no primary basal magma ocean. And I make a difference between primary basal magma ocean that have been proposed to keep core very hot and with a layer of liquid that is still maintained due to the liquid, between that primary basal magma ocean and a secondary basal magma ocean. If you reverse, if you do overturns, then you can bring down some material that may remelt. But this is after this process occurred, and I will go in more details, but this is different than primary and secondary, I think, in terms of the thermal state of the Earth initially. So why is that? I just put, these are pictures I have put before. Why is that? It's because anyway, the core cannot be very hot, and as we discussed already, this you have to create a certain amount of crystallization. Viscosity is rather in favor of not much fractional crystallization. So it means the mushy, before you reach the viscous transition, the mushy mantle crystallizing progressively is going to be relatively homogeneous in composition on a large range of depths. It seems people tend to agree in general when they look at the thermodynamics, because the basal magma ocean has a very interesting idea, but it's not based on looking at the melting diagrams. It looks like everyone that has, and I didn't put here again the Miller diagram, but everyone has been considering that at the tendency to reach that conclusion. And this is a busy diagram I will take time to explain. This is the density contrast between the solid and the liquid, based on the modeling of the densities of the assemblage of phases for the mantle and assemblage and the assemblage molten for the liquid. So the zero here corresponds to buoyant melt, this region, and this region corresponds to buoyant bridgemanite grains. This is the depth here, mantle depth, and those blue lines, they correspond to the degree of partial melting. So this corresponds to 30% volume percent of grains, this to 40% volume of grains, and the rest in the liquid. Initially, the melt is buoyant. When everything is molten, the melt is buoyant. When you create a few grains of bridgemanite, and I assume here that the iron will partition entirely to the melt. So this is, if you create some MgSiO3 grains, initially for F is 0.99, the melt will be buoyant and the grains will fall. So in most of the case, the grain will fall. If you want to make a melt denser, you have to increase the number of grains that crystallize. You have to increase the iron density in a melt. And a melt with a lot of iron will become denser. But it will become denser, the melt will become denser only when you have 30% of crystallization. And even though there, with 30% of crystallization, there is a huge range of depths where the density contrast is nothing. And if the density contrast is nothing, you don't have a fractional crystallization. So the melt will not go down here before you have built a layer of grains on the top of the core. But here you're not going to bring the melt down. It's extremely turbulent. And then if you want to have a higher a higher density contrast, you have to increase the fraction of grains. Here is 45% of grains. And then you have neutral buoyancy at mid-mantle depth. So you can reach neutral buoyancy, solid liquid, when you have a large amount of fractional crystallization. But again, there is a huge range of depths in between where it's neutrally buoyant, basically. So the idea of saying that you have a layer of bridgemanite that is built on and that the grains will aggregate because they're less dense or more dense to the bridgemanite layer is very difficult to achieve. You can achieve that in immobile, in a stagnant magma ocean, but that's not what occurred. So it's extremely difficult to build that. If you want to segregate something, as I mentioned before, you will segregate the bridgemanite to the core, not the opposite. But after you crystallize a lot, then you can make after you crystallize a lot, you can make where is it? The melt denser, but you need a lot of crystallization. So I'm not sure I convinced you all. It's okay. But I don't think the basal magma machine is plausible in terms of the phase diagram we've drawn. And I'm not sure it's very plausible to say we bring a bridge manganite thing and we get it there. The bridge manganite aggregates and you have a liquid on the bottom. This is very difficult to achieve, and this, nevertheless, whatever happens, makes the core relatively cold at the end anyway. The second implication is related to the thermal history of the core and to building a magnetic field for the last 4 billion years. There's been 2 papers published in 2015 about what should be the thermal state of the core early on based on the conductivity of the core, of the outer core. This is based on this diagram where today if we assume, based on the thermal conductivity of the outer core, that we have a heat flux of 15 terawatts, then Labrosse suggested, but Davis suggested basically the same, and you have to assume the core has been removing heat from its body for a long time to a pace that it's rated here. And this means a lot of heat should be stored in the core initially. So these are different models using different conductivity values for the outer core, with high conductivity values here lead to a very hot core in the past, because along the core adiabats, if you have a high conductivity, you remove a lot of heat simply. So you have to have a core very hot in order to reach that value that is the core temperature at the CMB today here. So this is how much heat you need to remove in order to get that pattern, in order to get the magnetic field working on using the thermal convection mechanism. Of course, this value here can be moderated if you put a lot of potassium in the core, which is a source there, but it's not going to be such a high amount there. And this is for lower conductivity value, because you're certainly aware that there is a lot of controversy about those conductivity value in the outer core. This is another diagram saying basically the same kind of thing, but this is how much should be the CMB temperature 3.5 giga year ago in order to maintain that magnetic field, in order to maintain that flux. And this is related to the age of the inner core. And here you see that the model needs some CMB temperature 3.5 gigayears ago as high as 5,000 K, and a very young inner core, because the inner core will only pop up here at the end of the story when the core cooled down. However, according to the diagram I've shown you, this is the only range available. I've been showing you diagrams where the core temperature has to go down until you reach the liquidus. And the liquidus is there. So this very early on, just after the moon forming impact, this is where we started. We didn't start it here. Yes, you started here when you make the impact, and you can melt everything. But after the Earth's, the cooling of the Earth has slowed down, and the mantle became viscous, we're not here. This is completely out of range. This means that the temperature, the core is going to melt everything on its path, because you have too much heat. You go out, you're above the liquidus, you're above the melting curve of bridgemanite. So you're going to melt everything, and the flux is going out. You can't keep a core to that given temperature for 1 billion years. It's totally impossible. So you have to start there. And you have to go to that point now where we are. And it means, based on those arguments, thermal conductivity has to be small. It has to be small, because you can only go from here to the current value I will show you in the next diagram during the 4.5 billion years. And this means that this diagram with a very young inner core is probably wrong also, because you don't have much cooling. So this is temperature that is plausible or possible after the moon forming impact, and we are here. So you have a circular cooling that goes from here to there, circular cooling of the core. You can't do more. So, of course, there are different mechanisms to make the dynamo in that temperature range of variation. You can have chemical solution from the core. You can have chemical buoyancy now that the inner core is building up. You can have some thermal conductivity, convection, that as we work out. And this, just for the pleasure of it, I want to share some ideas about the mechanical forcing mechanism that has been proposed 50 years ago, but it's been always neglected to my view, and I will show you a couple of slides. What it is, it's the fact that precession, tides, and nutation on an Earth that is deformed is having an implication on the movement in the outer core. In order to make a dynamo, you want movement in the outer core, and you can induce those movements by those movements. And there are many analogical experiments. I have a small movie for you here. This is an experiment performed in USA, but there are several others. Here the overall Earth is shaked, and you will see the movement organized. If you are somewhere on the planet, underneath your feet, the core is going to have an oscillating movement, and this has been proposed to be sufficient to participate to magnetic to the geomagnetic field. So that's a possibility which doesn't need fast cooling, doesn't need the super adiabatic gradient. You can have, by doing this, you can have movement in your outer core without being super adiabatic and highly convecting core. So this could be a mechanism that is still occurring today a little bit to participate with the others to maintain the core until present. Because there is something very special there that I discussed with Labros, of course. He's a friend of mine, but if I can go back. I hope I did a mistake. The philosophy of saying that today is 15 terawatts and tomorrow less is that the magnetic field should stop now. Because if we need 15 terawatts today, tomorrow we won't have the 15 terawatts. So the geomagnetic field should stop in the framework of the convection mechanism keeping the core working. With other things like the chemical segregations and the mechanical forcing, it explains why the dynamo is still available today. It's because we have a moon. So the moon is far. Does it play a major role? Does it control? It's a big question. But mechanical forcing is certainly an interesting point. Cool. Okay. And just again, for the pleasure of it, the mechanical forcing is intrinsically unstable and based on turbulence. This is the kinetic energy stored in that box of fluid that is compressed and there's tides and turn and squeezed. And there is some, you can see the movement here visualized during the rotation. That the kinetical energy is built and released and built and released, and this is intrinsically unstable. And that may be important for the thermal evolution of the Earth of some plumes and things like that. This is pure speculation. I have a further implication if I have time. I don't know, I may be long, but I have a further implication related to that diagram. If we now accept even with some overturns, maybe you can put some material there, but it won't change too much the temperature gradient. If we accept that the primordial temperature gradient was this one, so it's inverted in depth because this is geodynamicists use more toward surface diagram, rather we use as a mineral physicist toward the core. It's a different view, but so that's the opposite. But this is the mantle solidus toward surface. So this is the primordial temperature gradient after the moon forming impact, and today we are there. this is an enormous amount of heat. This is to remove from a solid mantle. You have a solidified mantle here that is still a mush, but viscous. And this is the 2 days configuration with a 1,500 degree temperature difference here. This is an enormous amount of heat on a superadiabatic mode or regime that you need to remove from the Earth. And this is initially also the radioactive elements are more active, so you have also additional heat from the mantle itself. And the claim here is in 2 or 3 slides. The claim is when you compare, this is today, and I will come back in the past before, so a little bit complicated sequence. Today you have those continental here, temperature gradient, the oceanic temperature gradient. You have some low velocity zones here, and some low velocity layer here, so the upper mantle is partially molten, most probably due to the presence of volatiles, which make it easy to melt partially, at least in some regions, the mantle here, probably correlated with deep melts or things like that. In the past, there's been work being done here about what was the temperature in the past of the mantle and the temperature profile. The surface potential temperature was higher by 200, 300 degrees compared to today. This is temperature today. Temperature was there. Also the composition of the lava has changed a lot, meaning that the melts were done in a deeper part of the mantle. So what we claim here is that if you increase the temperature of the mantle, if you have a lot of flux going from out of the mantle due to the Archean, in Archean time, due to the evolution from this mushy mantle to here, maybe the mantle has been molten partially in the upper mantle for a long time, maybe for all the Archean. So we correlate this with this many calculations. We don't have a clue on why plate tectonics started, of course. These are articles about that purpose. What we only say is that we have 2 different thermal regimes. There's a thermal regime initially with a superadiabatic mantle, a high flux, and a high mantle potential temperature that probably have produced a lot of melting in the upper mantle. That's one regime early. We have a second regime later where the temperature has gone down, and now we have only very small amount of melting due to the volatile elements, but not major melting. So my implication here is that the way the magma ocean has crystallized, building that mushy mantle and a lot of heat inside, has probably controlled how the Earth has evolved in terms of temperature evolution from the Archean mantle, very hot with a lot of melting, and today where the temperature has gone down, and probably it needs 2 billion, 3 billion years to remove all that heat that was potentially stored in the mantle initially after the moon forming impact. So these are my conclusions. I would go for that model. Maybe I would look like an old classical guy. I don't mind too much. I think it looks better, and it has a big advantage, this one, that if you don't melt the Earth completely, it's still okay, because you can add up some impacts, and you build heat inside. You have a large range of possibilities to keep along with that model. Overturns may happen. I think the temperature of the core has not been very high, rather small compared to previous model that was proposed, which also means that the inner core can be relatively old. To keep the dynamo, we need a relatively low thermal conductivity, maybe use of other gradients and gradients to keep the magnetic field working until present. And maybe the early Earth has been very has been the flux has been very high due to that primordial state in the mantle along the solidus, and maybe the Archean protozoa has been triggered by this evolution in the deep mantle. And on that, I want to thank you very much for your attention.
Right.
The upper mantle was molten for so long, and then
It depends what's the stagnant lead regime. If you melt partially, it means reducing a lot the mechanical correlation between the lithosphere and the astenosphere. It means I don't know what the fate of those melts. What we can say, what we know is that the difference in density between the melts and the solids is very little in that region of pressure. When the minerals didn't yet get to the denser form of the transition zone, there's those papers on the melt trap. Then today, the melt can remain trapped. The density contrast between solid liquid is small here in the olivine range. Then maybe the stagnant lead here has been insulated from the rest, so you may have some convection system underneath, but I have no, and we know some major eruptions. Maybe the major eruption, I couldn't go in that when I did the paper. Of course, comatite word appeared, but then it disappeared completely from the paper. And of course, comatite people didn't want such a speculative story to give a possibility for explaining those melts. But some melts were present in large amounts, so it could be related to that. I don't know precisely. It's a good question. Yeah.
so those are the. So the idea is you've got a 300-kilometer stack of lid.
No. In order to build the next diagram, what I did, I used so today it's a little more than that. Okay, the mantle potential temperature is 1650 K. Here is oceanic, here is continental. There are articles, in particular Michaud et al. Article, people from Paris, they claim that the Archean crustal temperature gradient was in between those. So what I do simply, I build it up. I build this first one, and I increase the temperature according to this one, and I reach that point. I think the starting lead would be on the top. Would be on the top. It means.
Well, that's kind of what I was thinking when I looked at that. Is that okay? That has to assume that you've got a big.
Just this one. 100 kilometers, 80 kilometers. You have this one, and underneath you start having some partial melting. So you have a stagnant lead. You could have a stagnant lead of 100 kilometer depth. Here, this is solid. All this is solid because the Archean profile is there. So until here, you're solid. And then underneath, you start with a partially molten mantle, which completely decoupled mechanically the stagnant lead from the convective mantle underneath. And so this is only the top with the flux of the heat flux going there and keeping the thing here. And if you would increase the flux, you would increase the melting, and then you would have probably some release of heat by melt going up. But so maybe this melting behavior here to a certain degree has monitored the heat flux you can get, because or how the profile, temperature profile underneath has been established during that time.
So this presumably, this kind of model will apply to other planets. And so if you the Venus, what would be the most critical thing?
Yes. Good question. I don't know. What I can say is there was not, or there was probably not a major moon-forming impact on Venus. Some people claim there might have been, but the moons have been lost. It's not impossible, but we can fairly think there was not moon-forming impact. So, to my view, and this is the philosophy of the talk, I think the core is a hot M member of Earth-sized planets, because we've molten probably almost everything. So, and Venus may have been initially a core that would be cooler or less hot. But then why is it still in a stagnant lead regime? I don't have an answer. I know there's been calculations on how the heat flow is occurring in Venus, and the radioactive elements are enough to bring the adiabatic flux up. So you can have this situation even with a normal adiabatic flux there, because you have internal heat. But I don't have an answer to your question.
Another question about the basal magma ocean. So, as the mantle is starting to still be a thermal boundary layer, core temperature stay hot despite what we can there always be a dramatic increase?
But when you use the basic equations for a convective system, your thermal boundary layer is fixed. The thickness of your thermal boundary layer is defined by the Rayleigh number, the viscosity, and everything. And so, if you want to have a possibility to separate, I'm not sure I understand well the question, but it's impossible basically to make a big temperature jump above the CMB if you're liquid. It's impossible. Like 50 degrees? This is the error bar. I agree. 100 degrees is the error bar, 200 degrees is the error bar. Yeah. But not a solid mantle, as I showed in one picture, not a solid mantle with a normal adiabat and a core. There is no way you can cross the solids, the liquids, everything there. Yeah, I didn't show you that part, but this is the CMB temperature. Okay, CMB temperature as a function of time. It happens that if you have the CMB temperature, then you can calculate the core temperature along the adiabat. So the inner core starts crystallizing here. The core starts to crystallize around this temperature. So today we have a certain size inner core that is related to the fact that we are below the mantle solidus by chance. It's just a coincidence. The coincidence is that the inner core starts growing when you look at the temperature in the core and where the core starts crystallizing. It's exactly there. Otherwise, we wouldn't have a core actually. But the inner core, we don't know what's going on in that region. But if you plot a straight line here, it gives you basically the green is superimposed with where the inner core should start crystallizing. No, but secular cooling would make basically a linear thing here. So it means the inner core will start on the middle at this edge. I don't have the diagram, unfortunately. It's here. When you have in the core, if you have a temperature higher than this one, it's all molten. If you have a temperature here, you start crystallizing the core in the center, and then you going down, you increase the size of the inner core. Yeah, but this was done with Illustrator, so I'm not sure it's straight. Yeah, I don't have an idea how it evolves from here to there. I didn't model it.
I'm wondering if, if I'm understanding correctly, after 30% magma ocean solidification, so the silicon metal will be denser than the silicon metal will go down. And
Yes, yes, and let me get to the point. Yes, yes, but after 30% of crystallization, the liquid and the solid gets naturally buoyant in this region of the mantle. Yes, that doesn't mean fractional crystallization. It means just they're naturally buoyant. If you want to have a liquid that is denser, you need to increase the degree of fractional crystallization. Yes, it's possible. This is why I don't overrule. I mean, overturns might be possible, but this is not going to affect much the temperature profile at the end, because temperature profile is already way down. You're already in between the liquidus and the solidus, and you're in the crystallization process. So you're going to be able to change a little bit how the mechanism of crystallization, maybe some chemical segregation here and there. That's not impossible. Yeah.
Thank you.